Here's the data from the lab. Basically, I just took if you look at the first data set here, I just found the mass of carbon dioxide that was lost after each period of time by subtracting the mass that you were left with from the mass that you started with. Then I had to go from the moles, so I went from mass of carbon dioxide lost to moles of hydrochloric acid consumed, and I used this equation right here. I plugged in these masses to where you see this box. So I went from grams of carbon dioxide, and I used the molar mass to go from grams to moles, and then from moles of carbon dioxide to moles of hydrochloric acid by using the balanced chemical equation. This is a mole ratio right here. And then from this equation, when I plugged in each one of these numbers, it gave me the moles of hydrochloric acid that were consumed. Now notice I have down here it says moles of hydrochloric acid remaining. In order to explain how I went from the moles of hydrochloric acid consumed to the moles of hydrochloric acid remaining, I'll give you an example of the calculation that I performed. So you can see how I got from this column, or this data set to this one right here. So if you see here the equation, I'm going to do timestamp 2, and I'm going to do 3 molar hydrochloric acid. So I plugged in my grams of carbon dioxide consumed, and then once I do my math in this stoichiometry, I'm going to get 0.001818 moles of hydrochloric acid consumed. In order to find the moles that were remaining, I had to find the moles that I started with. And then, so in order to do that, I had to multiply the volume of hydrochloric acid that was used, which is 50 milliliters, which is just what? 0.05 liters, right? So the liters cancel out, and I'm just left with moles. So when I multiply 0.05 times 3 moles, I get 0.15 moles. So basically, in order to get from moles consumed to moles remaining, I just subtracted the moles that I subtracted the amount that was consumed by the moles that I started with. So this would be 0.15 minus the number I found using this calculation right here. Alright, and let me explain why I decided to go from moles of hydrochloric acid remaining to the concentration of hydrochloric acid remaining. According to the source that I read, in order to determine whether it was zero order, first order, or second order, I had to graph the limiting reactant concentration versus time. Now I made a couple assumptions here. I had to assume that the hydrochloric acid was a limiting reactant just because, based on what you told me your teacher told you to go from either the moles or molar, or to convert mass loss of carbon dioxide to moles of hydrochloric acid, or the molarity of hydrochloric acid. So I didn't do the calcium carbonate as the limiting reactant. I made the assumption. The other assumption that I also made to go from moles of hydrochloric acid remaining to the concentration of hydrochloric acid remaining was that the volume of the hydrochloric acid was not changing very much, or minimally. So just to go from this data to this data, all I did was divide it by the volume that was first used, which was the 50 milliliters, but in order to get it into molarity, I divided it by liters. So moles divided by liters, which was 0.05 liters, got me from this column to this column. And from there, all I really needed to do was to graph the data. So you see what I have written up here. Zero order is the concentration versus time should give me a straight line. First order is the natural log of the concentration versus time should give me a straight line. And for second order, the reciprocal of the concentration, or 1 over concentration of hydrochloric acid versus time, should give me a straight line. So in the first graph right here, the first graph, all I did was graph the concentration as a function of time. So I took these numbers, I explained to you how I got those numbers, and graphed them: 0 times 2 times 4 times 6 times 8 times 10. Okay. And then, so I did each one of the graphs. I did the natural log of the hydrochloric acid. This is the natural log down here. So all this data is right here is the natural log of the concentration. See the function, you see ln of the concentration up here, B13. So, and then this data right here is just, again, the reciprocal, or the 1 over the concentration. That's all this data is right here that I graphed. So then I added a best fit line to each one of the data sets. So I'm going to remove this trend line so I can show you how I added it. I don't know if you're working with trend lines in class, but this is how I was taught to determine if the data set was close to being a line or not. So each one of the data sets were graphed with a scatter plot. And then I added a trend line, and I needed it to be linear. And then I also displayed the R-square value for each one. So I had to go through and display each one of the R-square values. Now, the R-square value, I don't know if you've talked about this in class. I don't know how in-depth you've gotten into this particular unit, but the R-square value basically tells me how close the data is to that best fit line, that trend line that I added to the data. The larger the R-square value is, or the closer it is to 1, the more like a line that data is. So if this number were 0.2 instead of like 0.9195, a 0.2 R-square value would tell me that that data is not linear at all. But this R-square value is kind of close to 1, so it's somewhat like a line. But what I did for each concentration was, okay, so if you notice that in each case, the 6 molar is the purple, the 5 molar is green, the 4 molar is red, and the 3 molar is blue. I compared all of the R-square values, and the one that was largest is the one that's most like a line, basically. So let's look at the 3 molar. So here's blue here, here's the other R-square value, so 0.9973, 0.9968, and 0.9946, which is the largest of those three numbers, is going to give me the one that's closest to the best fit line, that's the most linear of the three graphs. And it was actually the second order graph for 3 molar hydrochloric acid. Now for the 4 molar, if I compare the three data sets, and I'm actually going to send you this file so you can look over it. For 4 molar, it looked like the best R-square value was the first order, so the natural log of the data, of the concentration. And then 5 molar was the second order again, and then 6 molar was first order again, comparing all of the numbers. Actually, hold on. 6, I don't know why I circled that. Hold on. This is 0.9195. no, sorry, for the 6 molar, it's actually not letting me move this box. Cuts. That is so weird. Alright, so that's the largest R square value of the three 6 molar hydrochloric acid graphs. So, I would actually say that this reaction, um, because this R square value is really close to this one, it's just barely above it. I would say that maybe there was an error somewhere in this data, and that this was actually supposed to be, second order for the 4 molar as well, and that would tell us that the order of this particular reaction was second order. So I can't vouch for this data being 100% accurate. I can say that this is the best way that I know how to do it. Like I said, I base some of my calculations on assumptions, like the hydrochloric acid being the limiting reactant and not the calcium carbonate, and also can't vouch for the validity of the data that was collected. Like I said, I think that even though this is showing up as a first order reaction for the 4 molar hydrochloric acid, I think it's probably supposed to be second order as well, which would make everything second order, which in my mind would make more sense. But hopefully this helped a little bit. Hopefully, like, I didn't confuse you more. I don't know if your teacher taught you this method. Like I said, this is the best way I know how to do it, but good luck with the rest of the lab, and just let me know what happens.